Hello. So today what we're going to talk about and learn about is something called related rates. And these are a really great type of problem in calculus because they're very applicable. They have a lot of real life situations where all these problems come from. So you can see how math is centered in real life and how you might use calculus outside of a calculus class. So up until now, we've been learning about derivatives and we just learned about implicit differentiation. And the great thing about learning about implicit differentiation is that it's very important when you get to stuff like related rates when you have to take the derivative of equations that have a bunch of different variables in it with respect to another variable. So we're going to see how that works. So we can use the chain rule and implicit differentiation, that same process, to find rates of change for two or more different variables that are changing now with respect to time. So now instead of using d dx, instead of taking the derivative of a function with respect to x like we normally do and have been doing, now we're going to use d dt, where we're going to take the derivative of everything with respect to time. So in other words, how some variable is changing as time goes on, which is how we consider rates in real life. So let's look at a quick example just to kind of see how this works. So we're going to consider a particle that's moving along the curve x squared plus y squared equals 25. And all that curve is, it's a circle with a radius of 5 centered around the origin. So we'll just graph that real quick. So 1, 2, 3, 4, 1, 2, 3, 4, 5. So we're just going to quickly graph out this circle to see the path that the particle is moving in. So there's a rough circle for you. So we have a particle that's moving along this path. So it could be at any of these points at any given time. And the particle is moving at a rate of dx dt equaling 2 feet per second. So that means in the x direction, the speed of this particle, or the velocity of this particle, is 2 feet per second. And we want to know how it's moving in the vertical direction as well, dy dt. And we want to know when it's at the point 3, 4. So right about here, maybe we'll make that point in red to show how it's moving. So what we're going to do is, in order to find rates, we need derivatives. So the first thing we're going to do is we're going to take the derivative implicitly of x squared plus y squared and the derivative with respect to time of that 25. Just like we were doing in the last few videos with implicit differentiation, except now we're taking the derivative with respect to time instead of with respect to x. So now when we take the derivative of x terms, we also have to include that its derivative is not 1. We have to use the chain rule on all of our variables now. So when we take the derivative of x squared, we're going to get 2x using our power rule rather. But then we have to multiply by dx dt, the derivative of x with respect to t. Then we're going to do the same thing for y squared, so we're going to get 2y times dy dt equals 0, since the derivative of constant is always 0. So now that we have taken our derivative, we might want to solve for the rate that we're looking for, which is this dy dt over here. So we're going to isolate our dy dt and then we can plug in for what we know. So first we're going to move this 2x times dx dt term over to the right hand side. So we're going to get 2y dy dt is equal to negative 2x dx dt. We can divide both sides by 2 and cancel these 2's out. And then dividing both sides by y to get dy dt by itself, we're going to get that dy dt is equal to negative x over y times dx dt. And now all we have to do is plug in for what we know. So we know that x here is equal to positive 3, so negative x is going to give us negative 3. Our y was at 4, and we knew that our dx dt was 2 feet per second, so 2 over 1 feet per second. So now all we're going to do is simplify this. So we can, if we multiply straight across for fractions, we're going to get negative 6 over 4, which is going to be reduced to negative 3 over 2 feet per second. Now, with related rate problems, it's very important that you include your units over here. Because if you don't include units, we don't know what you're talking about. Negative 3 over 2 what? Cows, squares, units. We don't know how the particle is moving, in other words, or if that -3/2 is referring to a position, a velocity, maybe an acceleration, anything like that. The rate of change of a volume. We don't know what you're referring to if you just put the number, so it's very, very important that you include those units. So now let's just go over some basic guidelines for how to solve a related rate problem, because they're not all going to be just here's an equation and here's some rates, find a rate that you don't know. They might just be a problem like here's all this information and not give you the equation. So your first step is you always want to go through your problem, which is going to be a word problem more than likely, and write out all of your givens. So write down everything that you know for sure is true about this. And then maybe write down what you still want to know, what the final answer of the problem should be, or other variables that you don't know what their values are, any of that. Now you always want to draw a picture if you can. Pictures are really great ways to visually represent all of the information that you're given in a word problem, and sometimes seeing it drawn out, the situation drawn out and what it looks like, can help you to put all those pieces of information that might seem unrelated into an equation that makes sense. So after you draw a picture and label everything you know and still label everything that you don't know, so maybe put some variables on there for what you don't know, you want to try and figure out an equation that relates the information you do know and the information that you want to know. Because that way you can plug in for things that you know and solve for what you don't know. So after you figure out that equation, you want to use implicit differentiation to take your derivative with respect to t, always with respect to t unless they say for some reason with respect to another variable. And then after, the most important thing here is after you take your derivative, then you want to plug in all of your givens. So then you want to plug in the actual numbers that the problem will give you for different values of variables or rates, anything like that. And then you can solve for what you want. You don't want to plug in to your equation with your givens before you take your derivative, because if you plug in numbers, you're going to have a bunch of constants, and your derivative of constants is always 0. So your answers are going to work out real funny if you don't plug in after your derivative. So our first example is that a pebble is dropped into a calm pond, causing ripples in the form of concentric circles. So maybe during the summertime you've gone for a walk, you've gone to a pond area, and if the water's really still, if you throw a pebble in and it falls straight down, it forms circles. And by concentric circles, we mean that they start out small and they get bigger and bigger. So concentric circles just mean circles within circles. And we know that the radius of the outer circle r, so if we go down here and continue on our picture, labeling this as R here, maybe we'll do it in a different color so it stands out. If we label that as R, we know that that's increasing at a constant rate of 1 foot per second. So I know that the rate of my radius, or my dr dt, is equal to 1 foot per second. So when the radius is 4 feet, so when my r is equal to 4 feet, I want to know what the rate of the total area of the disturbed water is changing. So in other words, I want to know the rate of change of the area, or I want to know my dA dt. So we have our picture drawn, and we have our knowns labeled and our unknowns labeled. And so now we want to figure out an equation that relates all this information. Well, we want to know something about the area, so we should probably use the area equation for a circle, which is a equals pi r squared. And this is especially a great equation to use because it includes both the area part of a circle and the radius of it. So all that information that we're given is going to be included in our derivative, and then we're also going to be able to solve for what we want to know. So now that we have our equation, we're going to take our derivative with respect to time. So using implicit differentiation here, we're going to get the derivative of a with respect to time, or dA dt, is equal to pi, since pi is a constant, it's not going to go anywhere, times the derivative with respect to t of r squared. So we're going to get 2r times dr dt. And now that we've taken our derivative, all we can do is plug in and solve for what we want, which is dA dt. And this problem is especially nice because we already have dA dt equals. So now all we have to do is plug in. So we're going to get that dA dt is equal to pi times 2 times 4 feet times 1 foot per second. Now all we're going to do is simplify. So we're going to get that our dA dt, or the rate of change of our area, is going to be 8 pi. And now all we have to do is write our units. So since I have feet times feet, I'm going to get feet squared per second. Should be a 2 and not an S. So our final answer here, the rate of change of our area of these concentric circles, is going to be 8 pi feet squared per second. And knowing that it's feet squared per second is very good, because if you know how to measure area, you know that the units on area should always be units squared. So it's good that our units matched up like that. So let's try another example. So now we have that a ladder that's 16 feet long is sliding down the wall of a house. The base is sliding out at a rate of 3 feet per second, and we want to find how fast the top of the ladder is sliding down the wall of the house when the base of the ladder is 8 feet from the wall. So let's think about what this picture looks like. What's really happening? So say we have a house here. We'll draw like half of the house. There's a window. Got our roof coming down, anything like that. Maybe a door over here. You can get as creative as you want with these drawings, but they don't have to be too eccentric, because it's just pictures to help you figure out what's going on. And we have a ladder that's leaned up against the side of a house. Here's our ground line. So when we lean a ladder against the wall of a house, we form a right triangle in here. So we know that the ladder is 16 feet long. So we can label the 16 as the hypotenuse, because that's where the ladder is. And the length of the ladder is not changing, so we can label the constant on our graph. So we know that the height is going to be over here, and this is the base. So we know that our base is sliding out at the rate of 3 feet per second. So we know that dB dt is equal to 3 feet per second. And we want to know how fast the top of the ladder is sliding down the wall of the house. So in other words, we want to know the rate of change of h. So we want to know what dH dt is equal to. So since we have a right triangle and we know how long the hypotenuse is, an equation that's going to work really well for us is the Pythagorean theorem. So we're going to get that b squared plus h squared is equal to 16 squared. Okay, so it might be helpful for us to know what b and h are. Well, the problem tells us that we want to know what dH dt is when the base is equal to 8. So first we can kind of plug into this equation and figure out what our value of h is. So if we plug in 8, we get 8 squared plus h squared is equal to 16 squared. So we get that 64 plus h squared is equal to 256. So then we get that h squared is equal to 256 minus 64. Do the math there real quick. So we're going to bring down a 2, carry a 1. We're going to go to get 192. So then we just have to know that h is going to be the square root of 192. Okay, so what is the square root of 192? Let's see, what perfect squares go into 192? So if we look real carefully, 192 divided by 4 is going to give us 48 times 4. So we can bring this down to make this 2 times the square root of 48, bringing that 4 outside. And then if we divide by 4 again, we're going to get bringing out another 4. This is going to become a 4 outside times 12. Bringing in another 4, we're going to get 8 root 3. So now we know that the height of the wall is going to be 8 root 3 feet when the base of the ladder is 8 feet from the wall of the house. So now that we know that variable, what we can do is we can use our implicit differentiation and find the different rates. So now we're going to take our derivative. So we're going to do ddt of b squared plus h squared equals 16 squared. So the derivative of b squared is going to be 2b times db dt, whoops, making a little bit of a mistake there, plus 2h times dh dt, which is going to equal 0 because 16 squared, even though it has an exponent, you're not going to use your power rule on it because 16 squared is just another number, another constant, so its derivative is going to be 0. So now we can plug in for what we know. So we know that we're going to have 2, and then b was supposed to be 8 feet, times dB dt, which was 3 feet per second, plus 2, and we just found that h was going to be 8 root 3 feet times dh dt equaling 0. So now we're just going to solve for dh dt and see what we get. So 2 times 8 is going to be 16. 16 times 3 is going to give us 48. So we can write a 48 here. So now we can move that over to the other side. So we're going to get 16 root 3 dh dt is equal to negative 48. And then we're going to divide both sides by 16 root 3. Okay, so these will cancel with each other, and we're going to get that dh dt is equal to negative 48 over 16. Well, 16 is a factor of 48, so we can reduce this to negative 3 over root 3, which we don't want to leave our radical in the bottom, so we can rationalize this by multiplying the top and bottom by root 3 over 3. So then we're going to get that this is negative 3 root 3 over 3. Crossing out those 3's, we're going to get our final answer is dh dt is equal to negative root 3. And now all we need to do to finalize our answer is write our unit on there. So our unit here is going to be feet per second because we're looking at the rate of change of a length. So when the base of your ladder is 8 feet away from the wall of the house, the top of the ladder is going to be sliding down that wall at negative root 3 feet per second. And the rate of change here is negative because as the ladder slides down the house, the height of the wall is becoming smaller. So it has a decreasing rate or a negative rate. Let's try one more example. So say you're filling a spherical balloon. So say it's your birthday party or your sibling's birthday party and you're helping someone fill up balloons. When you're blowing these balloons up, they're perfect spheres. So you're pumping in air to these balloons at a rate of 5 inches cubed over seconds. So 5 cubic inches per second. And we want to find the rate at which the radius of these balloons are changing when the radius is 3. So let's draw a picture first. So we got a spherical balloon here. And we want to know the rate of change of the radius. So if we draw a radius in here, we want to know what dr dt is. But we do know that the radius is equal to 3. That's going to be 3 inches. And we know that we're pumping in air at a rate of 5 cubic inches per second. Now, cubic inches is a great indicator that it's something to do with volume, because volume is always measured in cubic units. So we know that dV dt is equal to that 5 cubic inches per second. So since we want to know the relationship between the rate of change of the radius, and we know what the rate of change is of the volume, we want an equation that's going to relate volume to radius. So the volume equation for a sphere might be very helpful. And the volume equation for a sphere is just V equals 4/3 pi r cubed. So now that we have an equation, we have all of our knowns and unknowns labeled, and we've got a picture drawn, we're ready to take our derivative and start solving. So we're going to take the derivative with respect to time. So we're going to get that dV dt is equal to 4/3 pi, since those are constants, they're not going to change, times the derivative with respect to t of r cubed. So we're going to get 3r squared times dr dt. Now we're just going to plug in and simplify a little bit. So we knew that dV dt was 5 is equal, well, 4/3 times 3 is just going to be 4. So we're going to get 4 pi times r squared, so we're going to get 3 squared times dr dt. And we're going to leave that as dr dt since we don't know that, and that's what we're solving for. So again, now we're just going to simplify and solve for dr dt. So we get that 5 is going to be equal to 3 squared is 9. 9 times 4 is 36. So 36 pi dr dt. And now to get dr dt by itself, we'll just divide both sides by 36 pi. We're going to get that 5 over 36 pi is equal to dr dt. And so now all we have to do to finalize our answer is put units on it. So our final answer can be written as dr dt is equal to 5 over 36 pi. And our units here are going to be inches per second, because the radius is measured in singular inches, no power on that, and since it's a rate of change of time, seconds has to be in the denominator. So that's how you go about solving related rate problems. Some of them get a little bit more complicated. So your basic process is read the problem, draw a picture, and label everything that you know and what you don't know, and then try and figure out an equation that relates all of that information. And just like you saw in the second example we did, where we were solving for the rate of change of the height of that right triangle, we had to go back and solve for the height. So sometimes they don't explicitly tell you what all of your variable values are, but you usually have enough information to go back and solve through for them. So thank you so much for watching. I hope this helped. Have a great rest of your day.